Okay, 17.2. We're going to start by talking about a method called calorimetry, which is it's a really elegant but simple way of measuring heat changes. Okay, so calorimeter is a device used to measure the absorption or release of heat, so you can track whether heat was released or absorbed. It contains a known amount of water whose temperature change is measured. Okay, why would something like that be called a calorimeter? Michelle, yeah, calor means heat, right? And meter is like to measure. So you're measuring heat. It's like a thermometer, but it's different. It uses a thermometer. Okay, so I'll look over here at the diagram. This is the basic setup of a calorimeter. You have a styrofoam cup. It's nothing fancy. Okay. If you ever come across styrofoam cups, please give them to me because I'm ethically averse to buying new ones, but could use some more. Okay. So you basically have water. You know the mass of the water. You are measuring the temperature change of the water. Okay, and you know the specific heat of water. So if you know specific heat, and you know mass, and you know change in temperature, what can you solve for the water? Q. So whatever is happening in the water, you can measure how much heat it releases or absorbs. And so there are two things that could happen in the water that would cause the temperature of the water to change. How could you heat up some water? Milan? Yeah, you could add a hot thing to the water or a cold thing. And if you were to add a hot thing to the water, it would have a particular mass, it would have a particular specific heat, and it would have a particular change in temperature. And you might be able to figure out one of these things about that hot object based on how it affects the change in temperature of the water. We'll talk about that later. Okay, what else can release heat? A reaction. So chemical reaction could take place in the water. There's lots of examples. You could even have a chemical reaction take place under the water. Like sometimes you can like catch a little, like a nut on fire, for example, and you can have it heat the water, and you can assume that all of the energy stored in the cashew was converted to thermal energy, which heated the water, and then you can calculate how many calories are in the cashew actually. So there's lots of things you can do with this. You could also do other chemical reactions under there and have it heat the water. Okay, so what equivalence can we establish if we assume that the calorimeter is perfectly insulated, which is, of course, completely incorrect because it's a styrofoam cup. But it's not a bad assumption. Okay, but like lots of energy can get out the surface of the water, and also like styrofoam is a good insulator, but it's not a perfect insulator. Okay, a really good insulator. Anybody know what a really good insulator would be? Like when you have a like a really good thermos or water bottle, how do they insulate it so well? They call it double-walled sometimes. In between the two walls, Sean, is a vacuum. There's no matter in between the two walls of the flask, so it's harder. The heat can only transfer through radiation and not through convection or conduction. Okay, so we can decide that if this is perfectly insulated, all of the heat, and we're just going to assume the water's being heated just to make it simple, but we understand it can be cooled. If it's perfectly insulated, we can assume that the heat that the water gains is equal to, but opposite in sign from, the heat that the system lost. Okay, so actually we'll just say heat gained would be the same as the heat lost, except it would have the opposite sign because one was losing and one was gaining heat. Okay, so you could basically say, if it was, for example, you had a hot metal in there, you could say the water gained a certain amount of heat, and a negative sign, the metal lost a certain amount of heat. And one way to think about that negative sign is if we're thinking about this in terms of MCAT, we can't just write MCAT equals MCAT, because if they both have mass and specific heat are always positive. If they both had a positive change in temperature, like both temperatures went up, you could just say MCAT equals MCAT. But if one temperature goes up and one temperature goes down, this delta T will be negative, and the equation won't make sense unless you have this negative here to cancel out that negative, basically. Okay, we're probably not going to have to worry about this, that negative too much, because we'll just assume absolute values everywhere, but it's good to know why it has to, or why it should be there technically. Okay, can a calorimeter be useful if the temperature of the water decreased? Yes, definitely. You would just have that the water's losing heat and the system is gaining heat. And then just like up here, maybe you would put the negative sign on the left instead, but again, mathematically it's equivalent. Okay, when would you ever have the water temperature go down? Lucas, if you add a cold object, for example, like a cold piece of metal is a sort of an obvious but weird example, or if you have an endothermic reaction. So for example, if you had ice melting in a cup, you could, and we'll do this in AP, you could have a, you could figure out like how much energy is required to melt the ice based on how the temperature of the water changes. Okay, let's do a little bit of practice here, and we're going to spend some time processing. This is a lot of data. We're going to try to process what's happening, okay? So you have a calorimeter. I'm just going to draw a new one just so that we're all on the same page in terms of what's happening here. Got some water, okay? And you have a copper coin that's being heated, okay? I'm going to write hot, okay? It's placed in a calorimeter containing 32 grams of water at 22 degrees Celsius. Okay, and I'm going to write initial temperature here just to be really clear. Okay, the temperature of the water increased to 24 degrees. So this coin went in here and it heated the water. Okay, TF was 24.0 degrees Celsius. Okay, it's asking how many joules of heat were released by the coin. Okay, so the nice thing here is that it's actually a pretty simple calculation. We're basically just doing Q equals MCAT. We're looking at just the water and how it was affected. We're not really talking about the specific heat of the metal or mass of the metal, anything like that. We're just trying to find Q for the water, which is the same as Q for the coin with the opposite sign, but that's not what the question's asking about. Okay, so the Q for the water will be equal to its mass, 32.0, times its specific heat, 4.184, or 4.18 is fine, times the change in temperature, which is always final, minus initial. Okay, and so we get whatever we get for that. Okay, 267.52 sig figs, 268 joules. Okay, again, the temperature change is always TF minus TI, which will sometimes be a negative value. We'll talk about that, and it can be in Celsius or Kelvin because a change in temperature will be the same regardless of which unit you use. Okay, here's another one. This one's a little trickier, so let's draw it out again so we can understand what's going on. If you want to pause it and try it yourself, I would love for you to do that and get it right, or not get it right and need help, but it's always better to try it on your own first so you're pushing what you're getting, okay, what you're understanding. Okay, so we have a chunk of metal, and it has a mass of 65 grams. Okay, it's at 100 degrees, so its initial temperature is 100 degrees Celsius, okay? It's added to 100 mils of water, but we need to know the mass of the water. This should probably be 100 point just for sig figs. Okay, so 100 mils of water is 100 grams of water. Okay. It says the water is initially at 22 degrees Celsius. The final temperature of the water and the metal. So why would they have the same final temperature? Owen? Yeah, because a hot thing and a cold thing, the temperatures will get more and more similar until they reach the same temperature, and then the heat will transfer back and forth, but neither temperature will change, assuming it's insulated. Okay, so what we did was we took this hot metal, We put it in here, and then we track the temperature. So we've got a thermometer somewhere in here that's sticking out, reading the temperature, okay? And so it's noticing that it goes from, the water temperature goes from 22 to 32. Okay, what is the final temperature of the water? Sorry, of the metal. Preeti? 32. Good. Okay, so what we have here is a lot of data, and what we need to do with it is figure out how it relates. So we're always looking at Q. How does the heat that the water gained compare to the heat that the metal lost? It's the same, right? Because all of the heat that made the water warmer also made the metal cooler, because the metal was losing it and the water was gaining it. So we want to say Q of the water equals the negative Q of the metal. It would be like if somebody took some money out of their bank account and gave it to you, you might have like a deposit of point or positive 100. They would have in their bank account, it would say negative $100. So we would say one of them was losing and one was gaining. That's why one is negative, one is positive. Okay. Let's write out all the variables here. Mass of the water times specific heat of the water times the change in temperature of the water will equal, a mass of the metal, specific heat of the metal, change in temperature of the metal. We're going to do all the signs correctly at first, and then I'll talk about how you could do it differently. Okay, the mass of the water was 100 grams. We added that decimal. Specific heat of water is always 4.18. Change in temperature, final minus initial, 32.0 minus 22.0 is positive 10. Okay, now for the metal, we have negative. The specific, or the mass of the metal was 65, only 2 sig figs. Okay, the specific heat of the metal is unknown. That's what we're looking for. And the change in temperature for the metal is final minus initial. Okay, so its final temperature was 32, and its initial was 100. So that's where we're going to get some weird math here, okay, because it's going to experience a negative temperature change, negative 68 degrees. But because of this sign here, that will cancel. Everything on the left-hand side is positive, so mathematically it's totally appropriate, okay? So on the left-hand side, we'll get 418, should have been able to do that in my head, 418 equals 68. Do you guys expect the specific heat of the metal to be less or greater than the specific heat of water? Sometimes I can't remember a single person in any of my classes. Isn't that sad? Anyways. Oh, Caddy. Okay. At least I can laugh at my own jokes. Okay, 4,420. So the specific heat of the metal will be lower because its temperature changes more wildly than that of water, which you can see from this demo even. The masses aren't the exact same, but they're similar, and the metal experienced a much more significant temperature change. Okay, so what we'll see here is that the specific heat of the metal is 0.946, which I guess we should do 2 sig figs. It's really low. I guess that's right. Okay, let me know if it's not. Okay, some important things to note here are, if you want to be really fastidious about the signs and have a negative on one side and a positive on the other side, and then do all your delta t's as final minus initial and being okay with them being negative sometimes, you can do that. If that's confusing, it's also fine to assume that all of the temperature changes are to do basically the absolute value of everything, right? So you can say absolute value of Q water, and this is still true, will be equal to the absolute value of Q metal. But what you're going to get is that you're always going to do larger temperature minus smaller temperature, and everything will be positive. It's fine to do that. I think it's important to understand why the negative signs make sense, but if you would rather do it with all the positives, that's fine. Just don't mix them up. Okay, like you can't do negative 68 and then not have this negative sign.